When learning new mathematics, one of the biggest speed bumps for me is the big, hairy function monster. I love math, and I still feel a sinking in my gut every time I come up against one of these beasts. Now, if I really want to see what these do and understand how they work, my options kind of suck. Mostly I can just translate them into computerese and get back a dead graph. To make this a little easier, I built Playbook. The first thing to see here is that I can type the formula exactly like how it looks in the book. Another thing to see is that the graph on the right updates in real time. Let's give it a shot with a simple function whose shape I don't immediately know. Notice as we zoom out that the graph scales itself, so we can always see what the function is doing. In this case, we can see that it looks like a cosine that grows linearly. This shows the first principle behind Playbook: sensible defaults. Let's look at the second principle behind Playbook: visualization is king. If my function has two variables, I should see a 2D graph right away. So now, let's tackle one of those hairy monsters from before, the Dirac delta function. As before, the function looks just like it did in my textbook. I now know that I typed this right. We'll call this the third principle. However, a 2D graph isn't that useful in this case. N's more like a control parameter for a 1D function. So let's pin n, essentially make it a constant. On the left, we see all of the arguments to the function. We'll hover over n, click the pin, and now it's a constant. Then we can even change its value and see how the function changes. It gets narrower and higher as n increases. But what if n goes negative? Aha! The peak flips. This shows the fourth principle: explore by reducing dimensions. We can even dig into calculus a bit. I know that the derivative of x squared is a line, and that of x cubed is a parabola, but this feels discontinuous to me. A line and a parabola don't seem to connect. However, what if we generalize and play with the parameter? We can now see how a line becomes a parabola, a cubic, and beyond. We can even see the back end creep up, like an inverse function. This shows the fifth principle: everything must be real-time interactive. Now for a final boss, that closed-form driven harmonic oscillator. As before, we can play with its parameters to see what they correspond to. Frequency, phase, damping factor, and amplitude. But we still don't really know what's going on inside the function. What do these component pieces mean? Let's explore. When I hover over this first term, I see a graph that shows me what it's doing. And I can even see it overlaid on the original function, acting as an attenuating factor. And what's going on inside the sine function? Oh, I guess this inner term is linear. That makes sense. And what does a sine function do with linear arguments? Well, it makes a wave. This is the last principle: understand big stuff by breaking it into smaller parts. So go ahead and check out Playbook. It's still very much a prototype, so it's gonna break on you. And I've only really tested it on Chrome in Linux, OS X, and Chrome OS. Also, a lot of buttons are placeholders for future features, so they don't really do anything right now. In the meantime, check out the projects it was built on, and give me your feedback. Let me know what you'd like to see and what you've used it for.